And good morning to those of you in Europe. It's just about half hour past noon where I am, and probably late at night in the US and so on. So it's a pleasure to, first of all, be attending this conference, and I should begin by thanking the organizers, all of them, for a wonderful job that they have done to put together this event. And also thank them for asking me to chair this session, which is a pleasure and an honor. So the speaker this morning doesn't really need an introduction to this community, Professor Peter Beelen from the Technical University of Denmark. And he will give a first lecture, which is an overview of bounds on Ihara's constant. So Peter, please.
Thank you. So funny enough, I'll share my screen with the slides in a moment, but funny enough, I was allowed to work one day at the university this week, so I thought it was safer to do it here with more stable internet. But the decision was made by the powers that be that today they're starting to dig big holes right in front of my window. But because of this, I cannot hear you very well when you ask questions. So bear with me on that. But for now, the listening part hopefully will work fine. Okay, so let me get started here. Okay, so I would also like to thank the organizers here to invite me to give this this talk. It's a great pleasure to talk about a topic that I really like a lot. And yeah, let's jump into it, shall we? What it is all about is the development on since Ser's lecture on what is known as Ihara's constant. So this number nqg has already been introduced. So given a genus, given a projective, absolutely irreducible curve over a finite field with q elements, for a fixed genus, you can ask how many points can such a curve have. There's the Hasse-Weil bound. There are refinements of these bounds. And especially Ihara realized that if the genus becomes big, don't you have to divide by g? Yes. Okay, first typo spotted. So Ihara realized that if you look at large genus, then there will be the Hasse-Weil bound is not going to be attained, and you can do better than that. So, and indeed, here I should have, of course, divided by g. So that is Ihara's constant, and the big question is, what is A of q? So at the time of Ser's lecture, what was actually known? Well, Ihara proved, and independently, Zwassmann, Fladet, and Zick, they proved that A of q is going to be at least the square root of q minus 1 if q is a square. And this was achieved using various methods involving modular curves. So this was one thing that was known. What was also known very shortly after is that there is an upper bound, the Drinfeld-Fladet upper bound, which says that A of q is going to be at most square root of q minus 1. And this means that A of q is equal to this expression if q is a square. Okay, so then what happens if q is not a square? Well, it's open then, and it is open now. There has been a conjecture that perhaps if you have an odd exponent p to the 2m plus 1, that it might be p to the m minus 1. But already in the time of Ser's lectures, this was not known to be true always, because Ser proved that A of q is positive. Actually, it's a constant, not depending on q times log of q. And this already shows that if m is 1, Manin's conjecture cannot be correct. And also Zink proved in 1985 that if you look at a finite field with p cubed elements, where p is a prime, then there's a lower bound on that, 2 times p squared minus 1 over p plus 2. And this also proves that if this m here is 1, that this is not the correct expression. So okay, so how did Serre prove this lower bounds? He used this using class field towers. Now that is not my forte, so I don't want to spend too much time on it, but it is actually fascinating to look at the developments since that time in this area. So Serre in his book, in this new updated version of the lectures, he gives also an overview over what happens for small prime values. So let's just look at those numbers, because you can see the progress that has been made since then. So you can really see that the original lower bounds have been improved quite a bit. The techniques are quite similar. So you still use class field theory to produce towers, but the starting points of those towers are better and better suited to obtain a good limit. Also, Kunt in his PhD thesis, as I understood it from Ivan Duursma, he refined the methods, he refined the these Goloshavovich bounds slightly so that more function fields can serve as a starting point. And this was then used further by Duursma and Mak to obtain the currently best known lower bounds for A2 and A3. So yeah, so what do we really know from this? Well, certainly this Grünfeld-Vladet upper bound is not attained yet, but it's somehow getting closer and closer. So for other small primes, there have been also people working on this, and you can see here several values. Oh yeah, by the way, maybe I should go one step back here. So these Duursma and Mak results, these are the only one where I didn't actually type in the fraction you get. So these are still rational numbers, but the numerator and denominator are so big that it's not pleasant to see them on a screen. So this is why I didn't do it for these two values, but these are still rational numbers. Yeah, anyway, so for other small prime, various work has been done, and better and better lower bounds have been obtained through the times, through the years. I saw there was a request for small typos in the book. I think there's one small typo for one of the references, but I can put that in the chat later on. So, okay, so here we have several bounds using class field theory, the methods Serre used as well there. So this is for primes. So what about non-primes? So class field theory certainly has been used for prime powers as well, but I won't say much about it, and for the simple reason that there are other bounds that are stronger available in that case. But certainly many people have obtained interesting result there as well. So the motivation for looking at A of Q, well, you can just take the purely theoretical point of view, say it's a nice constant, so let's look at it. But there is also another reason for looking at it, and this really came from coding theory. So algebraic geometry codes, they have been mentioned already this week. And there's a very nice link that Goppa introduced, and this is truly beautiful, and you can get extremely good codes, at least theoretically. And for this reason, there also a lot of work was done right from the beginning about making these towers explicit. So trying to find explicit descriptions of these curves with many points. And one approach is, well, look at certain modular curves, x0n, that are given by explicit computable modular polynomials. So I won't use a lot of theory on these curves, but one thing that I will use is that if you have a pair of elliptic curves that are connected by an isogeny that has a cyclic kernel, let's say of order capital N, that data modulo isomorphisms gives rise to a point on this classical modular curve x0n. So these can be defined over the integers. You can find equations over z, like we have here, a small example. And then you can reduce these equations modulo various primes that should not divide this capital N. And then things work out. You get a curve over a prime field. If you then take a quadratic extension of the prime field, you get many points. that come from the supersingular elliptic curves. So that's all I need. And these were used by Schwarzman-Vladetzink and Ihara to find good lower bounds on A of p squared. Well, okay, so what can you do then? So if you want to produce the code, say, you need to produce for a sequence of levels, these capital N's tending to infinity, you would need these nice equations. But these equations get big, so there's a nice online table for these. So let me see if I can show it to you. So there's a nice table by Sutherland. So these polynomials are symmetric. And here we have a small one, the one I just showed you for level 2. So you only need to list, so to say, half of the coefficients, roughly speaking, and then you have to make it symmetric afterwards. But these coefficients are big. So if we just go to a small level like 8, then here are the coefficients, and you can see that this is already quite big. So that's maybe not, I mean, it works, but you can see the disadvantages as well of this. Okay, so that is one approach. So then you can play the same game with other types of modular curves. And for example, with Drinfeld modular curves, you can do the same thing. So this time you have rank 2 Drinfeld modules connected by cyclic isogenies. And this has the disadvantage at that time was actually it's difficult to find these polynomials. So remember here we have a bivariate polynomial with coefficients in Z. In the Drinfeld case, you get a bivariate polynomial with coefficients, in the easiest case, in FQT, the polynomial ring. But Q is also a parameter. So for concrete small values of Q, you can find various examples of these Drinfeld modular polynomials. But to the best of my knowledge, where you have Q as a parameter, the only closed expression that I'm aware of is if the level is this time a polynomial. If that is the simplest one possible, namely T, then here you have an explicit expression. And it's funny because it involves Catalan numbers and these kind of things. But now I'm jumping ahead in the history. So at that time, there was actually a very nice, interesting iterative construction that give equation of certain Drinfeld modular curves by Manin and Vladetzink in 1984. So also on that side, there are algorithms that can produce equations like this. So you have algorithms to get equations, but this all came from the modular world, so to say. Now, there was interested in these things also from the coding community, as I said, and this gave rise to a very different idea and led to a breakthrough in 1985 when Garcia and Stichtenoot proved that if you use the suitably chosen equation iteratively, then you can also produce, this time in the language of function fields, you can produce a family of function fields which recover the Ihara result. So how does it work? So what you do is you start with a rational function field, fq squared of x0. Then you add a new variable x1, and x0 and x1 satisfy an algebraic relation that you obtain by putting I is 1 here. So this is how x1 and x0 are related. So that gives you the next function field. After that, you have to add a new variable, x2. And x2 and x1 again satisfy an algebraic relation, which is practically the same. The only thing you have to do is now use I is 2. So you increase the indices, but the form of the equation is the same. And then you iterate this, and Garcia-Stichtenoot managed to prove that this gives you a tower function field where the number of places of degree 1 over the genus of the function field tends to q minus 1. And since we are working over fq squared, this is optimal. So this gives you an optimal tower. Now the story as I've heard it, but Henning is in the audience, so he can correct me if I'm wrong, is that the idea to use such an equation at all in this iterative way came from Feng. So he was interested in the codes, and he tried to make this explicit. He didn't use this equation. The equation he used was that, well, first of all, Q is 2. So you don't have exponents here, but then the Q was not 2, but the exponent here was not 2, but 3. So xi minus 1 times xi cubed plus xi equal to xi minus 1 cubed. And that equation, this is an interesting equation over F8. So you get a model of the Klein quartic with many points over the field with 8 elements. And if you iterate this equation, you will get many places of degree 1 in the resulting tower. But the problem was the genus. So I think also Garcia-Stichtenot worked out that the genus actually grows too fast in this example. And then Pelikan had the idea to say, well, let's actually make life a bit simpler. So Q is still 2. Let's lower this exponent 3 that Feng had to a 2. And why exactly he said that, I asked him, and he said, well, that he doesn't really know where the idea from, but maybe the muse inspired him. That's something he would say. And if you do that, so for Q is 2, you get exactly this equation, and this does work. And then it was generalized to any Q in 95 by Garcia-Stichtenot. So this is an interesting approach. It is not modular, and it gives extremely explicit, simple equations. So that is the interesting part. Okay. Now, what is what this gave rise to is then the definition of a tower over a finite field FQ, a sequence of function fields, one contained in the other. We should not have equality on the way. The extensions should be finite and separable. The genera should tend to infinity because we want to use this to get lower bounds on Ihara's constants. And then they showed that such a tower has a limit, a well-defined ratio of number of places of degree 1 over the genus. And then, of course, for any tower, a Q is bounded from below by this limit. And it's implicit that this FQ is the full constant field of all these function fields. And then the game was, well, can you find other examples of such towers? So here's one, but can you find others? And what does it take for a tower to have a positive limit? Well, I don't think it's really known what it takes, but what works in all these examples is something like this. So what you want is you want to control the genus. It shouldn't grow too fast. And you want many points, so many places of degree 1 in the function field language. So starting with the latter, so how do you get many places of degree 1? Well, what is nice is if you can find places from the first function field F0 that split completely for all these extensions Fn over F0. So you don't, strictly speaking, need places that already split right from the beginning. It's okay if you find a place in the 10th function field that splits completely. But anyway, this gives the picture. And this will give you many places. If this splitting locus is not empty, you can immediately see there are many places in the nth function field. Simply the number of the cardinality of the splitting locus times the extension degree. The genus, well, there's a similar thing that is nice. If you somehow can make sure that you have chosen your equation, that you're iterating in such a way that the ramification locus is finite. So that is a good thing if you can do that. So you can pick a place you wanted to ramify in some extension Fn over F0. And if this set is finite, you're at least on the way. Then you can use Riemann-Horowitz formula to at least express the genus of the nth function field in the first. But you have to control different exponents on the way. So Feng's example has a non-empty splitting locus. It has a finite ramification locus, but nonetheless, it did not work. And the problem was in these different exponents. So they become too big. So that asymptotically, the genus is going to dominate the number of rational places. So what do what is the way out? So what you want is somehow, this is not the way it was done in 95 and 96, but looking back, what you want is somehow that there exists a constant b such that this different exponent is essentially bounded by b times the ramification. So b times e minus 1 times the degree of q. And this is not an unreasonable thing to want. So if we have tame ramification only, then the different exponent is the ramification exponent minus 1. So then these things will work out. So I guess the degree q should not have been there. But anyway. Right. So if you also know that this ramification is b-bounded, then you can use this Riemann-Horowitz and immediately get an upper bound on the genus as well, where we have a certain constant that does not depend on the n anymore times the extension degree. So having all these things at the same time, that is what makes a recursive tower work. But maybe there are other examples where this is violated and they work nonetheless. But in a known example, this is essentially what's happening. Okay. So a good picture to have in mind is that really shows this recursive structure is that, okay, so we have this recursively defined tower, which we have F0, F1, F2, and so on. But what you really have is a pyramid of function fields. So this was in the paper 96 that I'm going to talk about in a moment. So this pyramid of function field, this really shows you how to use this recursion properly. So for example, if you're interested in the ramification locus, well, that means we have a place below, it ramifies somewhere. So let's say it ramifies in this step. Yeah, but then it had to ramify in this extension as well. And that can then be used to investigate what is going on, what the ramification locus is, because then you can use the recursion to do the backtracking and to see what the place over F0 was. So somehow all these things with finite ramification locus and splitting, this becomes most visible here. And if you understand really well what is going on in the base of this pyramid, so to say, then hopefully you can push all this information up and figure out what is going on at each step in this recursion. So this picture is extremely helpful, and it was in the second paper on towers by Garcia and Stieftenhout from 96. So again, there the game is that you have to come up with the right equation, and this one turns out to work. And again, it has a good limit. In fact, it is another optimal tower. So the expressions you see here, so this is like a trace from fq squared to fq, while on this side, if you multiply a numerator and denominator with xi minus 1, we get a norm and a trace from xq squared to fq. And this explains why we have splitting places at all. So if you pick any non-zero, well, a trace non-zero element from fq squared and insert it here, what you get is a non-zero element from fq, and you have to solve trace equal to such an element, and you get q non-zero elements in fq squared for the next coordinate, so to say. So this shows that indeed you have a splitting, a non-empty splitting locus. So here I've identified values from the field with places of degree 1. And similarly, the ramification locus can be seen to be finite. So this is an Artin-Schreier extension. So in the first step, you are only interested in poles of this, but then you have to do this backtracking, and it turns out you also have to add 0. So that is will also ramify eventually in this tower. And then you're not done. So as Feng examples showed, you now have to worry about how does the different exponent behave. So Garcia Stieftenhout showed that this ramification is two-bounded. So they didn't show it in 96. They did clever manipulation to compute the exact different exponent everywhere, which also resulted in the exact genera of all these function fields. But with hindsight, this is the key to show that this ramification is two-bounded. So then they proved, actually they computed the genus, but certainly it is upper bounded by this, and the limit now follows. If you simply compare the number of places of degree 1 with the genus, you can see that the limit of this tower is going to be at least q minus 1. And that's the optimal thing. So, okay, so this was a very successful approach. And just one word about this two-bounded ramification. This is what simplified the proofs considerably. So what the picture is that if you have two Artin-Shire extensions of, let's say, prime degree here, and you know that we have totally ramified places below. So this f prime is the composite of these two intermediate fields. So if you know that below we have totally ramified places and the different exponent is 2 times p minus 1. So meaning that in terms of ramification groups, that the second ramification group vanishes. Then the difficulty was always to figure out, well, what happens up here? Now, since this f prime over f is a Galois extension with Galois group z mod p times z mod p, you do know that E is 1 or E is p. But if E is p, then what is the different exponent? That was the difficulty. And what was the insight in 2005 is that in this setting, also up here, the different exponent is 2 times p minus 1. Sorry, there's something in the chat. Just a second. What does two-bounded mean? Yeah. So it means that the different exponent is less than or equal 2 times p minus 1 times the e minus 1. Okay, yeah. So this two-boundedness can then progress upwards, and then looking at this pyramid picture, if you know that everything is two-bounded below, you can push this up. That is the message here. Now, given the time, I think I should not talk about the proof, although it is a nice illustration of the use of Galois theory and higher ramification groups. But anyway, you can find it in the 2005 paper. So, okay, so I was jumping ahead a bit to give you an idea on how to prove these things. And but in the meantime, other things have been happening. Other recursively good towers were found, and this is one we will also see tomorrow a bit. So here's an example of a recursive tower that actually proves that Ihara's constant is positive, except possibly for prime fields. Of course, we know it's positive also in this case, but this particular construction works whenever you have a Q of the form p to the e, where e is strictly larger than 1. So this is in by Garcia, Stiefenoot, and Thomas. You have this equation here, gives you a good tower, but the limit is 2 over p to the e minus 2. So it means that Serre's result is going to beat this if q becomes large enough. On the other hand, if p is 2 and e is also 2, actually this gives you an optimal tower, a tower that meets the Drinfeld-Vladen bound. Okay, so and there are more examples of towers attaining this type of limit. So then what happens, among others, is that in 2002, Van der Geer and Van der Vlucht, they found a tower given by Artin-Shire extensions over a field with 8 elements, and the limit was 3 over 2. And this is a very nice result because this is actually things bound for this case. And again, the difficulty at the time was, how do you really prove that the limit is this? The splitting is not a problem here. The problem was, again, the genus. So Van der Geer, Van der Vlucht carried out detailed, careful computations to compute the exact genera. And it followed that indeed the limit is 3 over 2. This example can also be treated with this two-boundedness approach. And then the limit is, you can obtain it much easier, but not the exact genera though. So that is still needs this hard work. So this was generalized to the case p is not 2. So here's the equation you would need if you want to do this for any q. And you see in general, these are not Artin-Shire steps anymore. It's not Galois. which also makes the analysis harder to figure out what is going on. But what happened after that is Ibasa, Garcia, Stichtenoot found another tower that does have Galois steps, and then this two-boundedness result again helped out to prove this limit. So this is exactly again Zing's bound, although now Q can be a prime power, not just a prime. So far we have then found various towers, and the difficulty is always how to find the equation, and once you have it, prove that indeed it gives you a good tower with a positive limit. So in the meantime, there is still this other approach using the modular curves, and this is still an extremely relevant approach, especially because Elkies realized that certain modular towers are in a very natural way defined recursively. So how does this work? Well, so remember that if we have the data of two elliptic curves connected by a cyclic isogeny, so let's now say that the degree of this isogeny is a power of some capital N. So we have such data, and the isomorphism class of such data corresponds to a point on the modular curve x0 capital N to the n. But since we have a cyclic isogeny, you can split this up into smaller parts, and you can in this way split this up into n steps where the isogenies are cyclic of degree capital N only. But then if you look at two successive elliptic curves in this picture with this cyclic isogeny, then that you can interpret that, at least it gives rise to a point on x0n. So in other words, one point on this modular curve gives rise to an n-tuple of points. And how does it work with equations? Well, at least the first attempt, we know that if you take successive J invariants of these elliptic curves, then they satisfy this modular equation of level n. But now we have n+1 such J invariants, and this means that we get the same equation n times. So this already gives you a recursive way to describe these modular towers. So you can describe this one modular curve in some sense iterating the equation for x0 to the n. But there are some technical issues here. And I just want to point this out, what the real recipe is. So if you want to produce certain modular towers, so you have to choose this level capital N. But once you've done that, you start with the rational function fields, the function field of the curve x1, the J line, in other words. Then you add your first J invariant J1. There's an algebraic relation given by the modular polynomial. And in this way, you obtain the function field of x0n. And then what we would like to do is add another J invariance and use this same equation again. But this doesn't work because the polynomial you're then looking at is going to be reducible. And somehow we could have known that because what is the extension degree we are looking for? Well, then we would need to know what is the degree of the corresponding cover from x0 n squared to x0 n. Well, that degree is capital N. But the degree in one variable of this phi of n is larger. So this already means that it had to be become a reducible equation. You can also see it in a very simple way, because if you replace t by j0, it's going to vanish because these modular polynomials are symmetric. And we know that if we insert j0 and j1, we get 0. So indeed, this is a reducible equation, but there is only one factor of degree n. So if I remember correctly, the other factors can have degree at most n over 2. So there's no choice. You pick the one of degree n. So this is now really a trivariate polynomial, but this is the one you can then use to iterate and find the function fields of these other modular curves, x0 n to increasing powers. So that is, but note actually that this gives you a recursion of depth 2. So this is not the clean recursion of depth 1 picture that we had before. So there's still some work to be done before you can actually see that these modular towers, that modular towers can be defined with a recursion of depth 1, just as these 95, 6, and 7 towers. But this is what Elkies worked out. So he didn't quite put it like this. He used some other techniques, but he did use this similar approach and proved modularity of the at that time known optimal towers. So towers achieving the Drinfeld-Vladup bounds. Now I had planned to just look at a small example, but I can see that time is going fast. But nonetheless, I want to spend some time on this because what struck me also in Ser's book is he's not afraid of explicit computations if the need calls for it. So I also want to show you at least one. So what is the result? So we have this tower. It's one of the examples from this 97 paper I talked about. And this attains the Drinfeld-Vladup bound. And Elkies proved that this tower can be identified with a modular tower f4 x naught 3 to the n. So the function fields with you reduce modulo 2 and then extend the constant field to f4. And how does it work? Well, if we follow the recipe I've just sketched, what you do is, well, we need this modular polynomial for the level 3. Well, fortunately, we're working modulo 2, so actually it becomes very simple. Here it is. And the genus of x03 is 0. That was a key ingredient in Elkies' approach as well. So we can generate this function field by one element, S0. And just looking at this equation a bit, you can see quite quickly that this is the element you're looking for, or at least it is a possibility. And you can express J1 and J0 in S0 then. So this means that these function fields, if we go to x03 to the n now, what we would have done previously is we start with J0, J1 up to Jn. This would generate this function field. But since every S variable gives rise to 2 of those J invariants, we can also just look at S0 up to Sn-1 instead, where I've defined Si up here, just changing the indices in the expression I found for S0. So you can do that, and you can find an algebraic relation between S0 and S1, since we can express 1 over J1 in one hand in S0, but also by increasing the index here to 1, we can also express it in S1. So there's an algebraic relation between the two. You can factor this polynomial, and the degree 3 factor is the one we were looking for. So this equation here is gonna be useful to generate this modular tower explicitly. This is still not what we were looking for, so the equation we want is up here. But what you can simply do now is iterate this process. So also x09 has genus 0. So we can find an x0 that generates the function fields. And we do the same game. We can express S0 and S1 in terms of this x0. And now we actually find the 2 expressions we want. So remember, we're working modulo 2. So if you work out what this cube is, the ones cancel out, you get exactly this expression there. So now we can use the x variables, increasing index like this. We can use these x variables to work out what is going on and generate this modular function field by x0 up to xn-1. And the algebraic relation between the two is the one that was found by Garcia, Stiefton, and Thomas. So that tower, although it didn't arise from the modular theory, it has a modular interpretation. And Elkies pushed this further and also showed that the first 2 towers from 95 and 96 in this way, they also have a modular interpretation, but this time you need Drinfeld modules of rank 2 to do this. And this continued for a while. There were several other towers found. Some of them were modular, and in 2002, Elkies showed also modularity of those towers. So there's an article by, what was it, Marai and Stiefnoot and Wolftange, where they found several explicit towers when Elkies wrote an appendix to that paper showing modularity of the optimal ones. So that's an interesting topic. And Elkies expressed this fantasia that perhaps every asymptotically optimal tower of this recursive form must be modular. And certainly he gained evidence for this. Okay, good. Let's see. Yeah. So then, nearing the end of my talk. So the last thing I want to mention is then the latest update on the non-prime case. So also for the non-prime case, it is possible to find explicit recursively defined towers that give you a good lower bound on Ihara's constant. So what does the lower bound look like? In first form, you can choose your Q to be any prime power. You can choose a J and a K that have to add up to N and have to be relatively prime. And given that data, you can find an explicit tower. This time the genus computation is more involved than ever, but so it's not easy, but the splitting is easy though. So, but what was shown is you can actually obtain this lower bound here. So it's kind of a harmonic mean of these two quantities here. And the equation is rather simple. I'm cheating a bit here because this is actually a reducible equation. So you have to choose factors to actually produce the function fields. But in this shape, it is quite a nice shape. And so if you want to optimize this result, well, first of all, if n is odd, the best you can do is to choose Q to be the prime P you're interested in. So n is odd, the exponent j and k, you simply round n over 2 up and down, and that's your choice of j and k. Then you get the best possible result from this. But actually, if n is even, you can also do this. So imagine that here we are interested in AQ squared. Well, what you can do is choose j and k both equal to 1. But what you then actually get is Q minus 1. So then you recover Ihara's result again. Actually, that's not surprising if you choose n equal to 2. This equation gives rise to the 95 recursive tower. So that's why. Yeah, but for n odds, you actually get this bound, which is, to the best of my knowledge, the best lower bound that's known at the moment. But n, well, with one exception, namely n is 1. So if n is 1, there's a problem with this formula, because then here you have p to the 0, so you're dividing by 0 here. You can still give meaning to this, but the only meaningful way for this expression would then be 0. So for n is 1, the lower bound gives 0. So that is, of course, not the best known lower bound. So Serre showed that A of p is positive. So this is where the class field theory towers are the best. But for all other n, this gives the best known lower bound, to the best of my knowledge. So for example, if n is 3, this simplifies to Singh's bound. So Singh's bound seems to be a special case of this. Okay. So I have a little left, but I don't think I have much time left. So what I wanted to say is a little bit about how to interpret these equations. So it is possible to obtain this equation using modular theory. So as Elke's already showed, that this 95 tower is actually, you can interpret this as a Drinfeld modular tower. And using the theory of Drinfeld modules of higher rank, of rank n, to be precise, you can also understand where these equations come from. But I think given the time, I should not go through those technical definitions. So I think I'll stop here. Thank you. So I tried to talk about the past and a little bit about the present. And then tomorrow I want to talk a bit more about the present and have some guess about what the future directions might be in this area. So, thank you.
Thank you, Peter. Beautiful talk. So it's open for questions, comments.
Peter, you described the story quite well, I just wanted to point out one thing, namely this, how we found these equations, the first equations. You said it came from Fang, which is correct, Feng and Rao actually, but they were, they came from the coding side. Yeah, so this is an example where coding theory actually pushed forward the theoretical side.
Yeah, absolutely.
Really. Mm-hmm. Thank you.
Yeah, indeed. If you have several fields looking at the same problem, nice things happen.
See. Well, I think Felipe has a question. Do you want to say it? Which?
Okay, I can say it. I'm asking if there's any guess for the value of AP on PS prime. The obvious question.
Yes, indeed. Yeah, so no, I don't think so. I mean, based on on these glass field towers, I think it's extremely hard. I would actually not want to guess the value of AP for AP to the n if n is odd. I simply don't know. The lower bound there is good, but I really don't know.
A2 seems to be getting closer and closer to square root of 2 minus 1.
Exactly, yeah, that's true. So, and of course, if A2 is square root of 2 minus 1, then why would it not be equal to root q minus 1 for any q? Yeah, who knows?
Thank you.
More questions? Elisa?
Yeah, I have, it's more kind of a philosophical question, but I would like to know your opinion. So, I mean, after your talk and after some things that we discussed yesterday, we have this impression that the behavior of curves over finite fields is kind of different when we consider them defined over fp to an odd or even power. And here again, we see that the even power case is like much better understood, and the odd one is, well, is not that well understood. But my question is, why? Why do you think that they behave different?
Yeah, no, it's true. It's not just in this area, but also in behavior of hypersurfaces and whatnot. It is true. I mean, it just might be that there is something with this harmonic mean, that this is what is going on, except for the prime case. But I have no structural reason. I mean, if you look at the construction of these Drinfeld modules of higher rank, it works just as well for even and odd. It's just that the genera behaves differently. But it's strange. I mean, the problem is that this choice of I and J, the J and the K, maybe that illustrates it. The optimal value would be n over 2, but you can't do that. So that's somehow. But this is so circumstantial, and it's not a structural reason to believe that n even or odd is truly different. But certainly odd is more complicated. That I'll give you. The prime case seems to be even more so. Yeah.
Thank you.
I may have a question as well.
Yes.
I was wondering, I mean, maybe you're going to say a bit more tomorrow, but at some point, I mean, you and Irene Bao, and I think also about the work of Emmanuel Allouin with Marc Perret, you tried to find, like, I don't know, rule tricks to see how, I mean, we could like go and find equations that would give like good recursive towers, or at least how to improve, how to analyze if a given one is going to give an optimal tower or not. Do you know about other kind of references who tried this path?
I mean, Yeah, so there are various properties that, I mean, optimal is one thing, but let's say good. Let's say a tower should be good. So then there are indeed several properties that have to be satisfied, and some that probably have to be satisfied, like this finite ramification locus. This seems to be something that if you don't have that for a recursive tower, probably it is not going to work. Another thing is that a very nice observation that disproved first generalization of these explicit towers was that the degree in both variables has to be the same. It seems maybe obvious now, but at the time it wasn't. So there's an article again by Garcia-Stichtenhout on skew towers that if these degrees are not the same, the tower is going to be bad. You see, because of this norm trace form of the equations, Serre actually had a guess on how it might work for other finite fields, but that doesn't work. So that is one of the things. And there are also results on the way the ramification behavior in both directions. I mean, a recursive tower is really like a correspondence. You have a curve and you have two maps to the isomorphic curves. So then how the ramification in these two maps behave. There are some indications of that. But there are very few non-existent results in this tower business. So one is that there was as I mentioned in '97, this Garcia-Stichtenhout Thomas article, they had a construction that a priori could have worked for a prime tower, but then Lenstra showed that it doesn't. So that is also one of the few non-existent results of towers of a specific form. But indeed, I want to say a little bit more about that tomorrow.
Thank you.
Yeah, I may have a small question.
Yeah.
Mm-hmm.
So Elke's approach of showing these towers modular not only gives another approach to the towers, but also to the points on the towers. So does that work in every case where a tower was seen to be modular, that you have an understanding where the rational points come from?
Yes, I think so. Yes, I mean in the sense that they come from supersingular elliptic curve or Drinfeld modules, or but it's not only that the recursive equation itself could be understood to be some two descriptions of a modular correspondence, but also if you iterate it, he gave a precise interpretation of the function field. So not just the first few, but all of them. So then indeed it's completely understood what the rational places correspond for. That's what he really did.
Yes,
yeah.
I think so.
Questions?
I have another question. A long time ago, Lee and Maharaj did a computer search to find equations that could generate good recursive towers. And they didn't find any. But that was back in the, I think it was in the 90s or maybe early 2000s. It was a long time ago. And so computers weren't as good, and then the software wasn't as good. So I don't know. I mean, it might be something that could be tried again. Or do you know if it's been tried again?
Yeah, I mean, I know of, for example, let me think. So for example, there was a PhD thesis from Lutter from 2007, I believe, where he tried this again, also with some new insights on what kind of towers to look for, and he found several equations. So yeah, people have tried more, and a few more were found, also some optimal ones. There's one in particular I want to talk about. Yeah. So yeah, so people have tried again, but it may well be worth an effort to try once more. But the game has become harder. I mean, we have now these rather sharp lower bounds, and yeah, the question is, what is the goal? Do you want to improve those lower bounds, or do you simply want to find more examples of good towers? That is a little bit the problem, maybe.
So you don't seem to believe that the lower bound is the exact value for an
It,
arc?
it really depends on the time of day. I really don't know.
But Alp did. But
Sorry, Alp did?
that was the impression I had, I think, once maybe I...
No, in fact, I believe that the real value should still be the 25-bladed upper bound. But it's not based on anything. It's just that, I mean, there are just very few examples, and the chances of finding the exact value with the first non-zero example, or not first non-zero, but first close to the bound examples are not too high. And we're just looking at the examples where you iterate the same thing. So you're bound to get something rational, whereas the upper bound is irrational. So maybe just recursive towers, as we know them now, are just not enough to get anything irrational, or at least the calculation you have to do in much deeper detail to see that the values are in fact irrational and so on. And so it's also a hope that there's still things to do there. I mean, it's
yeah.
Okay, I believe it's the harmonic mean is the correct value because it's so beautiful. Yeah. So.
All right.
I like it. People are making brave conjectures here, not like these curves of fixed genius.
There's also another conjecture, which is, I think it was Winnie Lee who told me that she believes in it, is that Peter mentioned that for this harmonic mean, if you kind of make sense what happens of it for the case where the exponent is 1, it will give you a 0 there. Right? So then the idea would then be that the real value is this harmonic mean as the main term plus something logarithmic. And when the exponent is 1, you just see the logarithmic part, and that's what the class field towers would give you. So I conjecture that it's one of these 3.
Time will tell, hopefully.
Okay. There are no further questions. Let's thank Peter once again for this wonderful talk, and we look forward to the next one.
I will unfortunately not be able to go to Zulip now. I have to conduct exams the rest of the day. So sorry about that. I will try to read it later.
Good luck. Thanks.
Okay. Thank you. Bye.
Thanks a lot.